Okay, so in this video, we are going to find the derivative of the determinant in four different ways. The first is explicit method, in which we just first find the like determinant and then take the derivative. Second is Leibniz method, in which basically we try to differentiate row by row, and we take sum of all the determinants that are formed. In Jacobi method, there's an explicit formula that is trace of the adjoint of A times derivative of a matrix. In arrow decomposition, that means first of all we decompose this matrix into value form, and that simplifies out uh, determinant, and that's how we do it. So let's go one by one and let's see how interesting it can get. Right? Our function is simple. It's just like 1 1 1 1 1 in first row in column, 2 2 in second row in column, and 2 plus x square in third row, in third column intersection, right? Okay, so let's do it. We want to find the derivative of the determinant of 1 1 1 1 1 2 2 2 2 plus x square, right? This is a function, right? Basically, how you can say this is, this actually gives, this determinant actually gives an expression. So this is just like derivative of some function by dx, not x square, sorry, by dx. Okay, now the first way, the explicit way, first of all, just find derivative. So derivative will be 2 times 4 plus 2x square, right, minus 4, and then 4 plus 2x square minus 4, and then negative 1 times, this will be 2 plus x square minus 2, and then plus 1 times 2 minus 2, right, by dx. And this becomes d by, this is just 2x square, and this is minus x square, right, and by dx. So this becomes d of x square by dx, and that becomes 2x. And so yeah, the first one was easy. Basically, because it was 3 by 3 matrix, was determinant could be found easily, so that's why it was easy. But usually, if that's not the case, we either go with Leibniz method or Jacobi method if it's difficult to find determinant. Mainly, I think Leibniz will be more easier or better way. Now let's see Leibniz method. This was explicit way, right? Now in Leibniz method, what we do is, I'll just give you the glimpse first. Let's say we wanna find determinant of this, sorry, derivative of this determinant, where in the determinant there's just some, let's say, a1 of x function, a2 of x function, a3 of x function, and then b1 of x. I'm doing it for 3 by 3, but you can generalize to any kind of determinant, right? c1 of x, c2 of x, c3 of x. So let's say if you want to find a derivative of this determinant, okay, what Leibniz formula says is, okay, you first of all find derivative of the determinant with, we first find the determinant with the derivative of first row, right? We just take the derivative of first row, and in other row are as it is. Okay, so this the other row as it is, and then you add with it another determinant. Like now for simplification, like if I have to say like ddx of some a of x, or I will just write a prime of x. Okay, that's simpler. Now you just add with it another determinant, with now the second row being like differentiated. So b1 prime of x, b2 prime of x, b3 prime of x, and c1 of x. Now you can also generalize this to any dimension, not just 3, right? You get the idea now. Also now you add the determinant. Now only the third row will be differentiated. Okay, only the third row will be differentiated now. Sorry, c1 prime of x, c2 prime of x, C3 prime of x. So yeah, so this is what the Leibniz formula says. Now in this case, this for our purpose, our derivative of 1 1 1 1 1 2 2 2 2 plus x square. The derivative will be, first of all, derivative of just first row, derivative of 1 is 0, 1 is 0, derivative of 1 is 0, and the rest of them as it is, right? And then just derivative of second row. So 1 is 0, derivative 2 is 0, derivative 2 is 0, 1 to 2 plus x square. And then derivative of third row now, 1 1 1 1 2 2, derivative of 1 is 0, 2 is 0, 2 plus x square is 2x, right? Okay. Now the first determinant is 0 because the entire row is 0. Second determinant is also 0 because the entire row is 0. And third determinant is 1 times 4x minus 2, right? Plus 1 times 2x minus 0. Sorry, here's negative 1 in this case. And then plus 1 times 0 minus 0. So that gives us 4x minus 2. Oh, is that really 4x? No, sorry, this is not 4x minus, this is just 4x minus 0. I'm sorry. 4x minus 4x, and then minus 2x, which is 2x. We again get the same thing, right? Okay, so this way also worked, and we see that this way was slightly more easier because in that case the determinant we had to find was easier, right? So this is the second way, which is Leibniz way. Now let's go to the third way. So Leibniz way was basically just differentiating row by row and taking the determinant of the sum. I mean, sum of determinants, not determinant of sum. First row was explicit. Now let's go to third row. Third way. Third way is what was the third way? Jacobi's way, right? So 1 1 1 1 1 2 2 2 2 plus x squared, right? What do you do in Jacobi's way is, let's say if you want to find the uh, derivative of some determinant a, right, which is function of x, right? I mean, what I mean is, let's say a determinant of a is a function of x. In that case, this derivative can be found out using the formula. This will be equals to trace of adjoint of a times the derivative of matrix A. Now to find derivative of matrix A is actually easy. You just find derivative of all the elements, right? You basically find the derivative of all the elements in here, and that's the derivative of matrix, right? Matrix is basically you have a1, a2, a3, b1, b2, b3, c1, c2, c3. If you want to find derivative of this matrix, it's just the derivative of all the elements, right? And in traces, and let's, if you want to find trace of this matrix, right? If you want to find trace of, let's say, a1, a2, a3, b1, b2, b3, c1, c2, c3. Basically, trace is the sum of main diagonal elements, a1 plus b2 plus c3. So that's the trace. So yeah, so this is the formula, and we are going to use it. To use that formula, first of all, we need to find adjoint of A. So basically, now let's extract the matrix A first. Our matrix A in this case is 1 1 1 1 1 2 2 2 2 plus x square, right? Our adjoint, you know how to find adjoint, right? You just write cofactors of every term. So adjoint of A is a cofactor of 1. For that, just find a determinant of its minor, which is 4 plus 2x square minus 2, which is just 2x square. Also need to give the sign. Sign is basically plus minus plus, and again minus plus minus plus minus plus. It works that way. Now for 1, the minor is 2 plus x square minus 2, which is x square, but the sign is negative. For 1, it's 2 minus 2, which is 0. For this one, it's 2 plus x square minus 2, which is x square, sign is negative. For the center too, minor is 2 plus x square minus 1, so x square plus 1, and sign is positive, right? Yeah. And for that, for this two, it's just 2 minus 1, which is 1, and sign is negative, right? Yeah, sign is negative. And for this left bottom corner one, it's 0. And for this bottom middle two, minor is 2 minus 1, 1, but it will be negative. Oh, it's interesting to see that this is becoming symmetric for some reason, right? Yeah, everything is becoming symmetric. That's interesting. Okay. And now for 2 plus x square, it's just 2 minus. Oh, even the original matrix is symmetric. So yeah, that makes sense now. Okay, for 2 plus x square, that's just 2 minus 1, which is 1. And sign is positive, right? Yeah. Okay. So now this is the adjoint. And a prime will just be basically, since all are constant, that will be 0, 0, 0. That derivative will just be 0. And for the last limit, it will be 2x, right? Now their product, we need to find product of adjoint and like derivative of matrix and then take the trace. So now product of adjoint of A times derivative of them, like derivative of A matrix. This is just 2x square minus x square 0 minus x square plus 1 minus 1 0 so 1 times 0 0 0 0 0 0 0 0 2x, right? And now this will be that will be 0, that will be 0, that will be 0, that will be 0. If we take the product, I'm just taking the product, okay? That will be 0, that will be negative 2x, that will be 0, that will be 0, that will be 2x, right? Now I have to take trace of this matrix, right? And I have to take trace. So trace of adjoint of A times A prime is just trace of this matrix now. 0 0 0 0 0 0 0 minus 2x 2x, and for trace just add the diagonal elements 0 plus 0 plus 2x, and that's 2x. And we know that this is just the derivative of a determinant of A, so determinant of A derivative is 2x, and that's what we were waiting for, right? So this is the third way. So we use the formula that the derivative of a determinant is just trace of adjoint of A times derivative of matrix A, and that worked. This seemed to be harder, but sometimes it's actually useful. This mainly statistics, where we need this formula. Basically, we want to find the derivative of the log of or determinant, right? And in this case, we use the first of all chain rule, like derivative, determinant of A, and then this prime, and we use the formula that prime is just trace of the adjoint of A times matrix prime, and then we take determinant inside and becomes trace of adjoint of A by this determinant times A prime, and we know this is inverse, so it becomes trace of A inverse times A prime. So yeah, this does give a good formula in statistics. Is this what I saw you right now? But yeah, sometimes it can complicate stuff as well, as we saw here. Now let's go to the last way. Last way is using the LU decomposition, right? Yeah, okay. LU decomposition. I actually already have the LU decomposition with me right now, but it's not that hard to decompose it into a lower triangular and upper triangular matrix, right? So if we decompose into a lower triangle, upper triangular matrix, we will basically have 1 1 1 1 1 1 0 0 0. This is a little bit simpler. 1 1 1 0 1 1 0 0 x square. So this will be the decomposition. Now, what we are trying to do is we're trying to figure out this determinants prime, right? Now we know that since determinant of a product is product of determinant, so what you can do is you can basically try to write it as product of the determinant, product of determinants, right? So this becomes, first of all we find the product of determinants of two determinants, right? And then find the derivative. Now since this first thing is just a constant, we are trying to use the properties of derivative, that constant can be taken out, so we can take that out actually, right? So yeah, in this case it's simplified, so I'm trying to use this way because it simplifies a lot. So yeah, I could just use the properties of determinant, right? So I could take that out. Now it's derivative, right? This basically prime means the derivative. Now this constant is out, and now this is a little bit simpler, like to find derivative, right? We can again use the explicit way, but yeah, I was just trying to show you that there could be some benefits of using arrow decomposition. Now its derivative is just 1 times 1 minus 0, so just 1. And inside it's like determinant is x square minus 0, just that, right? If you like take determinant along this column, and after that just take a prime, so this is just 1 and this is just x square prime, and that's just 2x. So you get 2x again even after arrow decomposition. So yeah, it's beauty of math that no matter what you do, you always get right answer. So yeah, so using 4 ways we found the derivative of determinant to be 2x, to be 2x, to be 2x, to be 2x. And that's it for today. Hope you enjoyed this video, guys. If yes, do share with the friends as well. Keep learning, keep enjoying, and I look forward to seeing you in the next video.